Okay, let us recall what we did last time. So last time we talked about evaluation maps. So the space. So essentially, we fix tropical curve, which is graph with some directions, and it is also decorated by some integer vectors, some vectors b, which are primitive normal vectors to compactifying hyperplanes on leaves, some vectors n, 1, 2 internal edges, 3, 5, and then we kind of discuss what happened if you add mark points, and we talked that we can treat this kind of tropical curve decorated with a mark point as a kind of tropical curve with additional two valent vertex, and we checked that all our kind of consistency conditions, like conservation of these integer vectors and kind of moduli, so all this nicely works if we kind of on top of three valent vertices, which are usual vertices for a smooth tropical curve. So if we add two valent vertices corresponding to two mark points. Then kind of the moduli space of such tropical curve with the mark points have the very similar structure to moduli space of tropical curve without mark points. So kind of presence of mark point just adds an additional internal edges. So for each mark point we have an additional internal edge. So it means that previously we have like one single length key for this long edge, and now we have something I think we call it t plus and t minus. So pair of positive real numbers that describe the lengths of pair of lengths of this pair of new edges created by kind of treating this marked point as a two valent vector. So therefore, kind of on our moduli space, we say a tropical curve decorated by single mark point. Tropical curve in some toric variety X. So this moduli space was essentially okay. So for a fixed gamma and fixed decoration, so this thing was essentially kind of a Cartesian product of the following structure. So we need to fix position of some selected special vertex. Let's call it in orange. So let me just for the sake of simplicity, just choose this vertex as I think we call it the center of mass. Or you can just think of it as some kind of specially selected vertex, and that is this kind of image we call VC, image of VC X. So that is this vector in moduli space, and then for each internal edge of this graph, we kind of add length and kind of twist. And here, for each internal edge, this graph gamma, that was our tropical curve decorated by a single mark point, or we can say that it is graph gamma with a single two valent vertex. That was our moduli space. And then, kind of on this moduli space, so it is very simple. There is only single mark point. So we have a single evaluation map. But let us, just for the sake of unifying notations, let us call it evaluation map at a mark point 1. So basically what it does, it returns image, so it returns image of max point 1 in X. And to construct this image, we have the following way. So we know that this kind of part of the moduli space is essentially a coordinate of this center of mass value. And we had this equivalence relation that allowed us to move the center of mass vertex around and move it to any other vertex. And we have this kind of prescription how to redefine the image given this other data on the moduli space, which is this integer vector labeling, directions, and lengths. So that's what we can do here. So that is our vertex VC. And to get to our mark point 1, so what we need to do, we need to travel from vertex VC on this graph gamma. So it is a tree, so there is a unique path between vertex VC and any other vertex. So this kind of blue depicts this path from VC to vertex 1, and then we need to modify the kind of position of a center of mass vertex as we traverse this path, like as we traverse in edges on this path. So in this simple example, we just traverse a single edge. So what all we need to do, so for a radial position, so here the radial position that belongs to Rn and position in the torus, which is phi c. So for a radial position, since we are traveling, our path kind of has the same direction as the direction assigned to this edge that we call d minus. So therefore here we are taking this vector assigned to a minus, which is m1 with a plus sign, so it is m1, and then we just multiply it by a length of this edge, so length we will call it t minus, and that is kind of how the center of mass position modifies if we reassign this center of mass vertex to marked point 1. And similarly, for angular direction, we do things in exactly the same way. So we take angular position, and we also take the very same integer vector assigned to it, but now we multiply by kind of twist by minus assigned to this edge. So that is evaluation map. So here we have like a radial position. So this part kind of belongs to the kind of radial part of this toric variety, and we have a torus fiber over this radial part, which is some kind of polytope. So and this thing belongs to some n-dimensional torus, which is 1 to the n, or just n-dimensional torus that is fibered over this radial. So that determines the image of this marked point 1, and that is what essentially evaluation map does. So it takes a kind of a particular tropical curve, which is a point on this moduli space, and then kind of evaluate what is the image of marked points of each marked point in X. So given this evaluation map, so we can kind of generalize this construction if we have n marked points. So if we have a tropical curve decorated by n marked points, so then we have multiple evaluation maps for each marked point. We can kind of move the center of mass vertex to each marked point, evaluate the position using the same rules, and then we will get an evaluation map. So that map is X. And then we can use this evaluation map to pull back differential forms from X. So to a differential forms. Okay, so this evaluation map preserves degree of the form. So let me specify that the degree of the form stays the same, and here will be differential form from this moduli space of tropical curve with n marked points. So now, given kind of tropical observables, and that we also discussed last time, what is the tropical observables. So just recall. So to get kind of idea of tropical observables, we took Fubini-Study form, and then we used this exponential parameterization, and kind of took exponential parameterization, and then took limit epsilon goes to epsilon kind of stays positive and goes to 0. And from Fubini-Study form, which was something very smooth, and actually it is invariant under rotations on CP1. So it is something smooth with support of a whole CP1. So this procedure provided us a singular differential form in this toric coordinates R and phi. So what we got, okay, so some normalization that I don't recall right now. So some normalization. Okay, so let's say that we choose the phi such that the Fubini-Study form integrated over the whole CP1 just gives us 1. So then here in this normalization we would get the following thing. So it is delta function in radial coordinate here multiplied by the article. So we can check that if we also integrate over P1, which is in this case is kind of infinite interval, we took an line and kind of compactified it by including infinities. So this integral over P1 became just integral from minus infinity plus infinity in radial coordinate, integral from 0 to amplify in angular coordinates. So if we take this form and integrate it, so we will also precisely get the same normalization one. So that is a typical tropical observable. So it is u1 to the power n invariant differential force with singular support. So we kind of believe that it is possible to generalize this construction for non-singular support, but for now we kind of treat it with a singular support. So here singular support is kind of reflected in this idea that the support in this radial direction is just, so this form is only non-zero at a single point r equals 2. So we take bunch of such tropical observables. So in the case of CP1, just observables like this, and then we apply. So we usually call this tropical observable gamma alpha, or sometimes if we have like discussion, if we simultaneously discuss complex case and a tropical case, so we usually indicate gamma alpha tropical to kind of like label that it is tropicalization of some complex observable gamma alpha. So let us for now keep this notation. So we kind of take pullback map for mark point alpha for a tropical observable gamma alpha. So that gives us a differential form on a moduli space. So we can multiply the differential forms. So we have n mark points and observables. So we perform this pullback map for each observable, multiply the result. We get some form of degree, which is sum of the degrees of original observables on a moduli space, and then we integrate over this moduli space for kind of fixed type, and then we perform summation over different decorations. So our kind of full moduli space tropical curve of degree beta is kind of compactification of a union of this and mark point compactification of a union of the moduli spaces for a particular kind of decoration of this graph at particular choice of integer vector, and then we kind of compactify by adding kind of edges, internal edges of zero length, and kind of take a union of different types and compactify the thing. So and here, kind of in most of the cases, if we are insufficiently, for extensive remark, for sufficiently generic observables, we can ignore compactification part. So here, when we treat the integral over this full moduli space, which is this complicated object, by adding some kind of singular curves where internal lengths are zero. So generally, you expect that maybe there is some contribution from this integral on this kind of compactifying strata. However, for sufficiently generic observables, we can just ignore this compactification part and really kind of integrate over each individual moduli space and just add up result. So here, an example of sufficiently generic that we also talked last time. So we looked at example which is performing this integral of a moduli space for a simple setting where we have degree 1 tropical curves. So x was b2. So kind of beta, which is curves class, was just 1 times hyperplane class in H2 of B2. So H2 of B2 is one-dimensional, so it is generated by this hyperplane class, and you take a tropical curve with a curve class 1 times H, and that was usually called degree 1 curve. So we already discussed what is the tropical picture of this degree 1 curve in P2. So here I kind of stressed this kind of simplification, hyperplanes at infinity. So I just kind of drawing a graph with leaves along the primitive normal vector. So and we kind of discussed the simplest enumerative problem. When we count a number of one curves, two generic points. So in this situation, our tropical observables is kind of essentially tropicalizing this pair of Fubini-Studi forms. So it was 1/2 pi delta function. So our radial vector is two-dimensional. So we have kind of one. So passing through 2 points and some kind of location of these 2 points in the storic variety X is given by rho 1. Okay. Explain it rho 1 phi 1 and say rho 2 phi 2. So to specify location of the points in the height of toric variety. So we need to specify what is the radial location. So for these points, the internal points, so they have like point 1. So it has radial position rho 1. So it is position on this two-dimensional plane. And we have like a torus fibered over each point, and kind of position on the torus is given by this phi macro. So that is kind of specifying this to specify numeric problem. So we need to give a position of this point. So we have rho 1 and phi 1, and similarly for a second point we have rho 2 and phi 2 on a corresponding point. Mark point 2, and kind of location of the torus is given by this pair of numbers from 0 to pi, phi 2. So then, once again, so here, because we are integrating top form on a moduli space, so here normally we would say that the observables corresponding to this situation, they are delta function. So they are forms that have singular support in both radial direction and angular direction. Let's say phi minus phi 1. And here, because it is a point, so it is a full form. So it is d2r. Let's be more careful. d_r1, d_r2, d_r1, d_phi2. So that is kind of Poincare dual. So that is Poincare dual. To point 1. So this Poincare dual form. So it is a top form, so full form, which is supported only at a single point. So in radial direction, it is supported in a point rho 1 on this plane, and in a torus direction, it is supported at a single point with coordinates phi 1. So, however, in kind of tropical picture, we kind of want to use this tropical observables, which are U1 invariant forms. So therefore, to get a corresponding so to get a corresponding tropical observable, so what we can do, we can average over U1 square action. So U1 square is a compact group. So therefore it has finite volume. So what we can do, we can take this form gamma tilde. So this gamma tilde, this kind of differential form on this x. So let me go coordinates on xx, and then so U1 square, because x is the toric variety. So U1 square is some subgroup of C star square, which acts on this toric variety. So therefore, we can kind of induce the action. Okay, maybe I should call it like this. So let's say phi g is kind of action of U1 on a toric variety. So therefore, the action U1 action, which is induces diffeomorphism of x. So we can kind of pull back differential forms on x with respect to this diffeomorphism. So we take kind of gamma tilde, we pull it back with respect to this diffeomorphism phi g corresponding to elements g in U1 square. So we get some differential form that now depends on g, so it depends on which map we use to pull back. And then what we do, we kind of integrate this object that has g dependence over this compact group. using Haar measure on this composite. And this Haar measure, we can choose it to be normalized by 1, and that's what we declare to be a tropical observable in this case. So we take this singularly supported differential form, and we average of a group A. Let us see kind of how what we would get. Let me roughly 1, DR2, D51, D52. So that's the answer that we expected to get. So it is kind of singular support in the radial direction and kind of uniformly distributed in angular directions, and they give kind of U1 action or U1 square action. So I think for U1 action previously we used, like, for multiplicative C star action we used multiplication by T. So kind of for C star square action we roughly acted with some kind of multiplication by T in some powers. So in this case, like R and phi, so we essentially introduced them as some kind of coordinates for exponential parameterization of V. So that's why U1 action, it kind of acts in a very simple way. So R1, R2, phi1, phi2. So that is now exponential parameterization for this pair of complex coordinates. And if we choose so element G, so G belongs to U1 square, so we can say that G is a pair of angles. Yeah, let me temporarily call them phi1 and phi2. So it is pair of angles, and this kind of action of element G on a point with these coordinates, what it does, it kind of just adds phi1, calligraphic phi1 to a phi1, and then calligraphic phi2 to a phi2. So then, if we take a pullback with respect to element G with gamma tilde, so what we would get, so all we need to do, we need to substitute this phi1 plus calligraphic phi1 and phi2 plus calligraphic phi2 into this expression, and what we get, okay, so this two-dimensional delta function works. So this radial part, it is not changing because this kind of diffeomorphism does nothing to a radial part. While for angular part, so previously we have expressions like this, and we need to shift phi. Sorry, I think I called this coordinates with an upper index. So let me notation simple. So because phi with the lower index was kind of location, radial location of a mark point, and here what we do, we will add just this vector phi, and then here we still have like dr1, dr2, phi1, phi2. And then now kind of Haar measure on the group G normalized by 1 is very simple. So it's phi1, phi2 divided by 2 pi square. So then what we do, we can integrate back to Haar measure over 1 square with phi 2 star gamma tilde. And this integral essentially becomes integral d phi1 d phi2 over 2 pi square. And here will be delta function phi minus phi1 plus this phi. And to kind of here we integrate all possible values of this little phi1 and little phi2. And this delta function, because it is a delta function on a circle, so therefore there always exists a kind of pair of phi 1 and phi 2, which will make the argument of a delta function vanishing. And it will vanish exactly once. So therefore here, what the result of the integration would be precisely 1 over 2 pi square. So this factor kind of stays, and this integral will just pick up like a single point where argument of the delta function vanish. And this 1 over 2 pi square that we get from averaging is precisely this 1 over 2 pi square. So essentially, averaging does the following procedure. So it takes this angular delta functions in kind of phi direction, and then turns them and averages this delta function over the circle and turns it into a constant function 1 over 2 pi. So both of them integrated over circle. So if I take just delta function of a single variable integrated over circle and integrate 1 over 2 pi over circle, I will get identical answers. So that's kind of a bit clarification to averaging procedure that I discussed last time. So therefore, like we take this kind of geometrically formulated enumerative problem about degree 1 curve passing through these 2 points. So we perform this averaging, get these tropical observables. Yeah, let me read it. I already. Yeah. That part as well. So then, kind of performing this integral for this case. So we perform moduli space integral. So we have pair of tropical observables. So we take relation 1 for a first tropical observable, we pull back second tropical observable with respect to relation M2, and we integrate over this moduli space. And then I think we performed this integral and we got a very particular answer. Let me just write it. Be careful, so just sure. The final answer was the following. So we identify the theta function of delta rho 1. Identify the theta function of delta rho minus delta 1 minus delta. So delta rho as a vector of rho 1 minus rho 2. So the final answer depends only on a relative radial position, and kind of the answer is either 0 or 1. So this satisfies the theta function. So in fact, it's positive. So it is equal to 1. If x is positive, it is equal to 0. If x is negative, and it is undefined or it is discontinuous at x equal exactly 0. So kind of rough plot for this set of x is the following. So that's my x, and it can x equals 0. The functions stay 0 and then jumps to 1 at x equals 0 and discontinues exactly at x equals 0. So for any positive x it is 1, for any negative x it is 0. So the contribution for this particular kind of type of a tropical curve with 2 marked points like placed on this horizontal edge and this vertical edge. So horizontal and vertical means that they are labeled by a particular primitive normal vectors. Here, primitive normal vector 1, 0. Here, 0, 1. So this single contribution is kind of either 0 or 1. So it is 1 if both these conditions satisfy, that the difference in vertical position is positive. So difference in vertical position means that the point 1 is kind of above point 2. And it is 1 only in the case when horizontal position is negative, which means point 2 is to the right of point 1. So it means that this contribution is non-zero only in this situation that point 2 is kind of above to the left of point 1. So that is picture. So that is delta rho 2. So that is difference in vertical position, and this part is delta rho 1. So this contribution is only non-zero when point 2 is kind of above to the left of point 1. And you can geometrically imagine that that's precisely a situation. So if I put like pair of points 1 and 2 on a plane with this condition satisfied, so then you can easily draw a kind of tropical curve, unique tropical curve passing through these 2 points. So what you can do, you essentially like, okay, draw a horizontal line through a point 2, draw a vertical line through a point 1, and then kind of you will get intersection point somewhere, and here you draw a 45-degree line. And this drawing is precisely possible only if delta rho 1 is negative and kind of delta rho 1 is negative and delta rho 2 is positive. And if one of these conditions is violated, so if you have a situation, say delta rho 1 is positive, so delta rho 1 is positive, and say delta rho 2 is also positive. So in this situation, the picture would be like this: point 2 will be to the right and above point 1. And in this case, you can't draw a curve like this. So you need to draw some different curve, maybe something. Okay, let me think. I accidentally drawn not generic case when they are on the 45-degree line. So and here to kind of get some kind of tropical curve, we can draw it like this. So and that would be a different type of markings, because here marking 1 is still on a vertical line, but the marking 2 is on a kind of leaf or edge with a different primitive normal vector b. And we kind of, at the end of the class, we talked that there are exactly kind of 6, okay, so there are like 12 types of decorations for a pair of marked points, and 6 decorations where a pair of marked points are on the same edge or an edge with the same primitive normal vector. So this kind of tropical curves, they contribute nothing to this full moduli space integral, because the product of these evaluation maps is exactly 0, and that we verified last time. And the remaining 6 types are precisely types where marked point 1 and 2 are placed on different edges. And these 6 contributions, they will have kind of similar type contribution. So they will be only non-zero for sort of special relation for special special property of relative radial position, and if we add up the 6 contributions, we will cover kind of almost all radial positions, so except situations when we have 0 argument for this Heaviside theta function, so that it is when it is ill-defined, and that is the situation which is kind of called special tropical position. And when previously I said that we consider counting number of curves passing through 2 generic points, so here generic refers not only avoiding 2 points coinciding, but avoiding 2 points that lie on a line whose slope equal to one of the primitive normal vectors. So that's kind of special cases that we want to avoid. Okay, so that was extensive review of what we did last time. So what is the plan today? So today we're going to kind of recap the very same integral over moduli space. Today we recap moduli space integral has an amplitude in certain quantum mechanics. So that is kind of plan today, and hopefully by the end of the class we manage to kind of reinterpret this example that we studied in details last. Okay, so in this plan we have a kind of several new words. So amplitude, quantum mechanics, and this additional word certain quantum mechanics. So it means that this should be quantum mechanics with some additional property. So here certain. Let me just explain it or label it from the very beginning. So that's what we will call HTQM. So kind of word certain isn't adding these 2 additional words, HT, so QM, okay, quantum mechanics. And HT stands for higher topological. So HTQM, higher topological quantum mechanics. And to be even more pedantic, because in the later lectures we will start talking about different types of quantum mechanics. So let me add this type A higher topological quantum. But for today, we can kind of temporarily forget about this type A, because there will be a single HTQM that we will describe today. But later there will be multiple types. Okay, so and to give a description of amplitude, I first need to describe what is the data of HTQM. So let me start with kind of brief motivation. At least for people who familiar with a bit of physics or familiar with kind of mechanics or quantum mechanics, so this motivation would be somewhat useful. I will try to be very brief to kind of avoid other people getting bored if they're not familiar with the stuff. So kind of how do we see quantum mechanics in this moduli space integral? So in this moduli space integral we have some kind of summation over these discrete types of graphs. So, and what we want to interpret, we want to say that our kind of graph that they essentially represent trajectories for particles with x. So when we have a tropical graph like this, it means that we have like one particle traveling from a left, another particle traveling from below. So they kind of interact or collide in this vertex, and then say they produce a third type of particle that travels in 45-degree line. And kind of vertex balance condition. It looks like some kind of momentum conservation. So you're probably familiar from mechanics course. If you have collision of particles, then kind of momentum is always conserved, and if collision is elastic, so then you have additional energy conservation. So here we for a moment ignore the energy conservation part, so it is not clear whether collision is elastic or not, but we still kind of have momentum conservation because there is no external forces acting on this collision. Okay, so and then we notice that the trajectories of particles so they essentially okay, so straight rays. So straight rays means that if I write down a kind of trajectory in some parameterized form, so it is something like this. So in between these collisions, so when particles kind of move freely, so their position changes kind of linearly with the time, and they are moving kind of in a direction which is labeled by this integer vector for each internal edge. So it's like a free particle moving with velocity m. And that's kind of a reason why we want to treat this vertex balance condition for these velocities as some kind of momentum conservation. So if particles are identical, then essentially momentum is kind of proportional to velocity of particle, and momentum conservation in collision will be precisely vertex balance condition for velocities. And different directions kind of indicate whether particle is incoming or outgoing for this collision. Okay, so and that is this kind of key observation that trajectories are straight rays. Because in ordinary mechanics, like in kind of classical mechanics, trajectories being straight rays mean the following thing. So if I look at kind of time derivative for this radial position, so then time derivative for radial position is just this constant vector m. So now in the Hamiltonian description, so this radial position, the change in a radial position equal to momentum, and kind of rest of the Hamilton's equations of motion is that p dot equal to some kind of derivative, or in this case, a multiple variable gradient of some potential. So in our case, vector p equal to a constant vector m. So that's why this thing is 0. And what we see here, we see some kind of free particles. And that is kind of not unsurprising, because kind of in classical mechanics, like if you recall Newton laws from kind of high school course of mechanics, so then we have this idea: if there are no forces, then particles just move with a constant velocity. And that's what happens here. Particle moves with a constant velocity, and by kind of explicitly calculating r dot kind of assigning momentum to R dot, we rediscovered this idea that in Hamilton description there is indeed no forces and the particle moves freely. Yeah? So now let us make one more step. So we already recasted our motion. So we recasted this motion with a constant velocity m as a solution to a certain Hamilton equation. So now from these Hamilton equations we can extract Hamiltonian function. So yes.
So what is this P?
It's potential. So in kind of Hamilton equation, you usually have like a Hamiltonian which is something. Yeah. It's equal to potential, and then Hamilton's equations they essentially become that R dot is P, and P dot is this gradient of the potential.
Because for our picture we don't have such.
Yeah, so we don't have potential. So because our P is just independent on time. So that's why we say that it is a free particle. So this condition kind of implies that, okay, so it implies that potential is a constant, so and we can always shift Hamiltonian by a constant. So this condition essentially implies that we can set V of R to 0. Okay, so here, yeah, let me even practice more general way. So let me write it as kind of function of P plus V of R. So the equation of motion for such Hamiltonian would be the following. So R dot will be gradient with respect to Q of this function of P, and P dot will be minus gradients with respect to radial coordinates for V of. So in our case, this P dot is just 0, and R dot is just equal to a constant vector m. So therefore, this function whose gradient is a constant gradient means that this function is a linear function. So our Hamiltonian is given by this simple formula, which is scalar product of m and p. So, or in coordinates, that would be like m1 p1 plus m2 p2 plus all the way to nth component of this vector times n components of. So that is kind of a bit of unusual Hamiltonian, because usually when we think of a particle, we take this function to be a quadratic function. And kind of R dot is usually equal to P, and P itself kind of its change in time is determined by potential. But in our case, R dot equal to a constant vector, and we can kind of generate this using Hamilton's formalism by taking a Hamiltonian that is linear in momentum. Okay, so that is kind of Hamiltonian description for a particle moving with a constant velocity equal to this vector m. So now here we have a word quantum mechanics. So we really want to have quantum descriptions of this kind of particles. And in kind of quantum description, we kind of quantize this momentum into kind of derivative with respect to radial coordinate. So in quantum mechanical description, this particles would be something like m d over dr, or let me just call this wedge with a radial gradient. So this thing now is differential operator on and function in our radial coordinate. Okay. However, kind of radial motion is not the only thing that that happens to our particle. So our particle has some angular directions, and furthermore, I think that is kind of not easily seen from this simple construction, because this kind of classical description works very nice for kind of ordinary coordinates, and kind of more careful view on this particle shows that we need to add certain fermionic coordinates. So we need to add certain supersymmetry. And kind of addition of supersymmetry will do the two things. So it will kind of promote this Hamiltonian, which is very simple, like m times gradient in a radial direction acting on functions. So it will promote this kind of supersymmetry. So it will do two things. So it will kind of promote our Hilbert space that for ordinary particles was just kind of some normalized functions. Okay, so some normalized function, L2 normalized functions on Rn. So that was our Hilbert space, and it will promote this thing to supersymmetric Hilbert space, which essentially promotes this function on Rn to a certain like properly normalized differential forms, let's call it like this. So normalized differential forms on Rn, and kind of Hamiltonian, that was m times gradient. So in supersymmetric case would be promoted to the following thing. So if you just have m times gradient acting on functions, and we want to kind of extend this thing to differential forms, so the natural extension would be the following thing. So it will be Lie derivative, so that is object that acts nicely on differential forms. Lie derivative for this vector, for a radial vector field with components m. So that's what I wrote here. So it is radial vector field. With components that are components of this integer vector m. So if we kind of look how this supersymmetric Hamiltonian acts on functions, then acting on functions with precisely like taking a gradient and multiplying by m. While on differential forms, this thing kind of gives us natural operation. So then we also need to include angular coordinates. So it means that we need to promote our kind of space where position, where location, where particle was located. So we need to promote it to Rn times S1 to the power n. And essentially we need to compactify this thing, so we need to kind of properly compactify it. So the position of a particle would be essentially a point on our toric variety. So it means that kind of a new Hilbert space will be some kind of differential form from X. So we will talk about kind of what we do with normalization a bit later. So let us for now say that it is some kind of differential forms or differential forms with a certain additional properties. Let me just kind of tilde to indicate this one. And for kind of Hamiltonian, we actually still want to keep the same Hamiltonian, so which is kind of Lie derivative in along this vector m in radial direction. Okay, and kind of reason why we don't include kind of angular motion, we will see it a bit later, but it is essentially related to this idea that we can always average kind of our observables, and we can also average our states over this U1 action. So U1 part essentially does nothing interesting. So that's why we can only keep. It is sufficient to just keep a radial evolution. So that was kind of motivation for what kind of quantum mechanics we consider that this kind of interpreting tropical curve as a trajectory of a particles on a straight line kind of motivates us for considering kind of quantum mechanics for this with a Gilbert space, like space of this, let's say carefully, with quantum mechanics on a vector space which is differential forms, and kind of time evolution is given by this operator, which is Lie derivative in kind of radial direction along this vector m.
Okay, and before you erase, I have some questions.
Yeah. Okay.
Sorry. It's about this one. I mean, if two marked points are on the same leg,
Oh, the same edge.
the
Yes.
same edge, then it's always the contribution is always 0. Or do you need?
Okay. Let's say it the following way. So if we are in 2 dimensions, then the contribution is always 0. So if kind of x is 2-dimensional, then kind of regardless of what is the compactifying hyperplanes, so you can show that kind of product of this evaluation maps always vanish. I'm not sure whether it holds if x is higher dimensional. That's what I don't recall. So maybe it still holds, maybe not. So that's what I don't remember. But 2-dimensional x.
Yeah, we also need to assume gamma will come to on top that degree, like point.
Yes. Yes. So that's we also need to assume that it is.
If they are not top degree, maybe we still have some.
Yeah, no. If it's not a top degree, so then the contribution might and will be non-zero. So since you had this question, let me kind of draw a case when this contribution is non-zero. So let me study the following kind of. So remember when we talked about enumerative problems in 2 dimensions, we have this idea that that we have like two types of observables in P2. It's kind of points, like curve passing through points, and another type of observables is kind of curve passing through some hypersurfaces. So another kind of observables is the 2 forms that correspond to hypersurfaces, or in the simplest case to hyperplane. However, we kind of never consider it kind of in details this hypersurfaces, because we had a divisor relation that essentially told us that insertion of this hyperplane observables just kind of equal to a degree of the curve multiplied by answer, where we remove this hyperplane observable. So let us kind of see what is the tropical version of the enumerative problem when we have 2 marked points, let's say like this, and a single hyperplane observable. So in the homework which I will drop hopefully this week, so you will be asked to show that kind of tropicalization of hyperplane observable will give us observable that is supported also on some 3-rayed star, which is kind of unsurprising, because hyperplane itself under tropicalization became 3-rayed star, and observable is essentially Poincaré. So kind of choosing different hyperplane observables, so will be like different hyperplane, different tropical hyperplanes will have different locations for this 3-valent vector. So and then the intersection of this yellow curve and our white curve. So here it happens in this yellow point, and that's kind of a point where we will insert like gamma tropical corresponding to this hyperplane. But I can kind of freely move this yellow curve without changing the intersection number. So I can imagine a situation that this yellow curve intersects our white curve somewhere here, and then I will have like kind of 3 marked points, and pair of marked points, points 1 and 3, will be on the same ray, and indeed you can show to get a kind of proper divisor relation. So proper divisor relation is that we need to somewhat sum up over possible positions of a marked point 3, and kind of to get a correct answer. So there will be indeed a non-trivial contribution when this marked point 3 is on the same edge as one of the previous marked points. But this contribution will be non-zero because the tropical observable corresponding to this hyperplane, tropical hyperplane, it will be a 2 form, and therefore there will be no kind of vanishing or cancellation that happens when we have pair of 4 forms. So that is kind of simple example where we have kind of marked moids on the same edge, but due to the fact that we insert different types of observables, their contribution is non-zero. And that's why I say that I'm not sure what happens in higher dimensions, because to make this thing vanish, we need like some kind of proper tuning between degrees of the form and kind of number of moduli. So in 2 dimensions, kind of with kind of top degree tropical observables and kind of moduli corresponding to position of this center of mass position in 2-dimensional plane. So that gives precisely like zero answer, because you don't have enough moduli to support this situation. So while in higher dimensions you have more moduli, because the radial position is higher dimensional. So therefore there might be some contributions. And similarly here, if you have kind of lower degree differential forms, that it's not kind of degree 8, when we have 2-point observables on the same ray. So then once again we have lower degree differential forms, so we can still get some non-zero contribution from limited moduli that we have. And only for a top degree contribution, when we need to have like all differentials for all coordinates, so then we just don't have enough moduli to support this.
Yeah. Is it possible that the terms cancel because of some commutativity? Yeah. Now it vanished because the degree is too high. But yeah. Okay.
So that is okay. At least I'm not aware of some kind of immediate cancellation property. So there might be, like in particular cases, there might be some cancellation, but I'm not sure whether there is some kind of generalization for this cancellation into some kind of lemma that under this and these conditions you will see this cancellation. So technically, when you write it in kind of coordinates, yes, some terms would cancel, some terms would kind of add and get multiplicativity factors, but I'm not sure whether there is kind of some universal cancellation property.
Yes, maybe in this even degree observables there will be
but kind of the story is that tropical observables, they are always even degree forms, because we are looking at Gromov-Witten theory on the toric variety, and kind of homologies of rhetoric variety, they're always even dimensional. So therefore here there is, and that's why here we kind of don't care about order in which we multiply these evaluation maps, because all these kind of forms, they are even dimensional.
Yes, my real question is how to show the UV boundary doesn't contribute. It's like maybe have we got a proof here? Why this complication doesn't matter?
Okay, I think we haven't got a formal proof, so I think here we relied on this idea that that at least in simple examples we can see contribution from UV boundary. So the contribution from UV boundary is precisely a contribution where like one of the arguments for this Heaviside theta function vanishes. And what we know that in kind of when people discuss tropical enumerative problems, they kind of always have this additional quote that the observables should be in sufficiently general position. So that's why kind of contributions from this boundary of a moduli space, they will impose some additional, like depending on codimension of the boundary, you will get a corresponding additional linear relations on the data of your observables. And additional relations means that they are not generic, because generic things, they don't satisfy any relations. So that was kind of our argument, that going to boundary of the moduli space is impose this relation, and we can always avoid these relations on observables by kind of saying the words sufficiently generic. That if he happens to run, like happens to have like pair of points whose delta rho 1 is exactly 0, so it means that the points are kind of on a single vertical line. We can say that if we change the position of one point slightly, we can always avoid this situation. So, and that kind of matches with this idea that all this interesting stuff like boundary components, they happened in some codimension.
So in the UV boundary case, in general, we always assume some generic position argument, not some explicit cancellation of different contributions.
Yes. So we usually just completely avoiding this contribution by moving our observable slightly. So I think that's the usual story. I think I really need to make a break. So maybe we can make a break, and then after the break, I will kind of give a formal definition of this higher topological quantum mechanics, kind of based on this motivation. So check. This is 11:09. Okay. Okay, probably we will also go today for a single long break. So let us make a break to 11:20. So 11-minute break, and then we will work for 1 more hour. Okay. Okay, now we can erase all this situational part for some physics remark, and let us go to arithmetic. And HQM. So our HQM is labeled by vector space V. Okay, let me check to write it in correct order. Match this D Q G plus minus G R and okay. Let me give a definition straight away for case of graphs. So HTKM is a collection of the following data. Such that. Okay, so we start with V. So V vector space. Okay, let's be more precise. Super vector space. So super can be understood as Z2 gradient. So Z2 gradient vector space means that V is a direct sum of V0 and V1, and we say that it is gradient 0 and this one is a gradient 1. Okay, so then Q and G plus minus, so they are differentials acting on V. And here differential means that the two properties are satisfied. So it means that it's odd operator. So odd operator means that this, okay, let's say operator Q, and the same holds for G plus minus. So it take like Vk and take it to Vk plus 1. So here like k runs 0 to 1, and we look at this plus 1 modulo 2. So it means that Q takes V0 into V1 and V1 into V0. So it kind of changes this gradient by 1. And that's what means to be kind of odd operator. For D2 gradient is an operator that changes gradient. So even operator is operator preserving gradient. But Q and G plus G minus are odd operators. That is part of definition of differential. So differential usually kind of increase some Z gradient by 1. And in our case, we are working in Z2 gradient, so there is no difference between increase and decrease. And the only invariant statement is for operator either not changing gradient or changing gradient. So, and second property, which is usual property of differential, that all these operators are important. So if I apply Q twice, and similarly applying G plus minus twice, I will get zero. So differential is an odd operator whose square is zero. So these three objects Q, Q and G plus minus, so all three of them are differentials, so odd operator, the square is zero. Okay, so then third object G. So G is bilinear pairing on V. So it means that G is the following. So we take kind of two vectors from V, V1 and V2, and kind of get say a complex number out of it. So pair of vectors v1 say v2, and we map them into their bilinear pairing v of v1 v2, which is just a complex number. So vector space with some kind of pairing, with a pairing with some additional properties is what we usually call a Gilbert space, which is space of states in quantum mechanics. So this kind of G and V is the usual data for quantum mechanics. So Q and G plus minus, they are some special operators in quantum mechanics, and we will see in a bit what is so special about it. So property 4, so all this like 1, 2, and 3, these are objects that kind of exist generically in quantum mechanics or quantum mechanics-like theories. So it's some vector space with a certain bilinear pairing and some linear operators acting on it. Okay, here we should specify that they are linear operators. Some linear operators acting on it. Well, property 4 is some property that requires significant generalization of quantum mechanics. And this property 4 is related to this last object mu. So mu is the following object. So it takes a kind of pair of vectors and produces another vector. So this mu, so this structure in mathematics we usually call multiplication. So taking two objects of the same type, taking two objects and producing a third object of the same type. Okay, so this multiplication we need because in kind of our quantum mechanics we not only have some kind of motion of particles, but we have this interaction of particles in three-valent vertices. So mu is kind of responsible for kind of encoding in terms of quantum mechanics the data about three-valent vertices. Okay, so that is kind of our data. So pair of differentials, bilinear pairing, multiplication. So now, okay, so for multiplication we want to require a certain additional property that our multiplication is kind of associative multiplication. Associative multiplication. So it means the following, that if I say multiply v1 and v2 and then multiply it with v3, so it is the same if I multiply v2 and v3 first and then multiply result by v1 in this order. So additionally, so for ordinary vector space, we can demand like commutativity property that mu of v1 v2 is the same as mu of v2 v1. But because we are working with this v2 graded vector space, so we will demand graded commutativity. So often, especially in physics literature, like graded commutativity for the word graded is replaced by super commutativity. So kind of commutativity on super vector spaces or commutativity on graded spaces. So this graded commutativity means the following thing. So our vectors. So here having a gradient means that for each vector we can assign an element in V2. So if we have like vector which is fit purely in either V0 or V1, so then we can assign for this vector. So mu is kind of multiplication that is linear, bilinear cross argument. So therefore we can always decompose each vector into kind of even and odd part. So therefore here we can think of these objects as objects with kind of pure gradient. So pure gradient means that V1 and V2 are either from V0 or V1 subspaces. And then graded commutativity means the following thing. So if I interchange V2 and V1, so then I generate sign that depends on gradients of V1 and V2. And the idea is the following. So if and this sign is equal to -1 to the power V1 and V2. So in particular, that implies that if one of two vectors is even, so it means that its gradient is 0, so then gradient V1 times gradient V2 will be always 0, because 0 multiplied by anything is 0, and -1 to the power 0 will give us +1. So therefore, even vector kind of always commutes with any other kind of vector. So, and okay, so and the only way to get this minus sign is to get in a situation when both of the vectors are odd vectors. So then parity of V1 and parity of V2 will be 1, and here will be -1. So and that is usual property for this like super objects, that kind of pair of parity 1 for fermionic or Grassmann objects, that they typically anti-commute. And we want like our multiplication to kind of obey this property, that if I interchange arguments in this multiplication, then there is a sign that is the same sign as this usual multiplication of super objects. Okay, so it is associative and graded commutative. Yeah, I think that is good. So here we describe it like all these objects in HTQM data. So super vector space, 3 differentials, bilinear pairing, and associative graded commutative multiplication. So now we impose certain compatibility conditions. So compatibility conditions between different bits of data. So if we have, say, multiplication and differential, like on, say, ordinary differential forms, so kind of wedge product is an example of multiplication, and the RAM differential is an example of differential. So then we usually have something like Leibniz property. So that the RAM acting on a product is kind of the RAM acting on a first factor multiplied by second factor plus first factor multiplied by the RAM acting on a second factor with some sense. So that is our first compatibility property, is graded Leibniz. And even though all 3 objects like Q and G plus minus are differential, but we only impose graded Leibniz for Q. So it means that kind of Q acting on a product of 2 vectors given by the following. So this is a plus sign Q acting on the first argument, and here we have an additional sign which is parity of V1, and here V1 Q acting on the second sign. So this graded Leibniz is very same graded Leibniz that we had for differential forms. Unfortunately, I need to write something with that part. Okay, so it's this property. So then we get kind of more interesting property for this G plus minus operator, which therefore I will call it differently. I'll call it 6. So this property it kind of has this boring name, 7-term relation for G plus minus mu. And the idea is the following. So if I take, so because the relation will be the same for G plus minus, let me just write it for G plus. And the relation has this interesting structure. So if I take G plus acting on a triple product, so V W U. So I first multiply V and W and then multiply it by U and then act with G plus. Then I get the following three terms. Okay, let me. No kind of way of writing. So G can act on a product with a plus sign. So then with some sign. Okay, so let me, for kind of the sake of saving time, let me just work up to a sign. So here will be some signs which you can look up in our way. So let me just write it structurally. So this thing will be 2WG minus acting on a product of V and U. Then there's also some sign mu2 V G minus on the product of the remaining pair. So these first three terms is that we multiply 2 of 3 arguments, act on it by G minus and multiply it with the third argument, and there are exactly 3 terms like this. So because this multiplication is kind of graded commutative, so there is no difference in kind of order of these arguments, and the kind of proper sign would compensate for that. So and therefore there is only 3 ways of choosing a pair up to order among 3 elements. So with these 3 terms, and then the remaining terms, they are of the following structure. So it's mu2, and here we act by G minus on one of the arguments, U and W, and similar 3 other terms. So G minus acting on V, on U, mu2, V and W. And then with the same sign, G minus acting on W, and here the 2 of U. So it is 7-term relation because it kind of involves 7 terms. So even though like both Q and G plus minus are differentials, but they behave very differently with respect to this multiplication. So Q is it's like obeys this simple Leibniz relation, simple comparing to this 7-term relation, and G plus minus obeys this complicated relation. So kind of to give you a hint, what is the origin of this relation? So this 7-term relation is kind of analog of Leibniz for 2nd-order differential operators. So Leibniz relation typically emerge when you have kind of 1st-order differential operator and mu is a multiplication. But you can imagine a situation that you have like 2nd-order differential operator. So 2nd-order differential operator means that it is kind of derivatives with respect to say 2 variables. D over d psi, d over dy. So to make it like psi is odd and y is even. So that would make it kind of odd operator, and because it has d over d psi, so it will naturally square to 0. And now if I have like vector space which are just functions of psi and y. So functions of kind of two variables or some collection of even and odd variables, multiple of them. So we can multiply them, kind of multiplication of functions. So then we can ask a question like whether there is some kind of relation between multiplication and this differential operator for it being second order differential operator. And it turns out that to get some sort of relation, you need to multiply three objects, and then by acting by the second order differential operator, you can, because normally if you act by second order differential operator on a product, then you will typically have two types of terms. It's like both derivatives acting on one factor or kind of derivatives acting on different factors. And when derivatives acting on different factors, you can't express this result through action of g. Through action of g on one of the arguments. And that's the reason why we need to have like a product of three objects. It is essentially to eliminate these situations when these two derivatives in second order operator acting on different factors. So if you take like this product of three objects act by g plus, so then indeed we would get like one of 7 situations like this when both derivatives acting on either one of the arguments or both derivatives acting on this product. But then if we kind of arrange our signs correctly, we would get a cancellation of the terms where these derivatives acting on different factors. So that's kind of how we can kind of guess and get a signs for this 7-term relation. So it is essentially kind of modification of Leibniz for second order differential operation.
But on the left hand side it's g plus, but on the right hand side it's g.
Okay, sorry.
Okay.
Sorry. Yeah, my bad. Yeah. So let me just call it g. So
okay. So they're the same.
Yeah, so they're all the same. Yes. So okay, so that was kind of compatibility condition between differentials and this multiplication. Okay. Okay, so now next step is compatibility condition between pairing and differential. Pairing and differential. So what would happen if I act with the differential on a first argument? So usually in kind of quantum mechanics we are looking into some kind of Hermitian or anti-Hermitian operator. So usually we want to relate this thing with an object like this with some sign. So that would be like hermiticity or anti-hermiticity for this operator with respect to bilinear pairing G. So and in our definition we want actually once again to choose these signs different for G. I think let me kind of here I forgot to put one of the conditions. So this bilinear pairing it should also somehow respect grading. So if I change the order of arguments, so then the result changes with some sign factor. So here what we want to have a sign which is -1. I think the parity of p, but let me double check because this sign is an important sign and then it's making mistakes. So for q we want a sign like this, and for g plus minus we want a sign to be different, to be like this. So that is property 7. So that is our kind of compatibility between pairing and differential. that we can kind of, when we have pairing of differential acting on one of the argument, we can kind of flip this differential to acting on other argument at a price of some sign that depends on the parity of the first argument. Okay. So then, okay, so that was compatibility condition between differential and multiplication and pairing. And the last compatibility condition is a compatibility condition between multiplication and pairing. So this condition is what people often call Frobenius structure. So it is essentially a property like this. So I can yeah, so we can do the following thing. So we can compose G and multiplication to get an object that takes three vectors and sends them to complex numbers. So I think for kind of various reasons we want to call it mu3 not. So because mu is secretly mu2. Multiplication of two elements. So to describe descendants, we will need multiplication on kind of n elements, and mu3 is kind of multiplication of three elements, but the result is not from a vector space, but for numbers. So that's why we put upper script 0. So it's kind of multiplication into numbers, and what we want like mu3 0 to be graded symmetric for all arguments. So that is compatibility condition between this pairing G and multiplication mu. So kind of Frobenius structure is usually a situation when you have some multiplication and pairing, and they are compatible in a similar way. Okay, so that was easy compatibility conditions. Now kind of less obvious compatibility condition. Okay, okay. So condition 9 is the following. So we define H, which is anti-commutator of Q and G plus. So that is kind of even linear operator in V, because Q and G plus, they are both odd operators, and when we anti-commute odd operators, we get even operators. Okay, let me add it here because I'm a bit out of touch. So for these differentials, we want this property that differential G minus and G plus, they anti-commute, and G minus anti-commute with Q. And that kind of Hamiltonian is the only remaining anti-commutator for among the pair of differentials. So because differential anti-commutes with itself, so anti-commutator of G minus with Q and G plus are 0. So it left us with the only remaining anti-commutator of Q and G plus. And this thing is non-zero, it's some linear operator in V. So now what we want, so we constructed this linear operator, and then then what we want to define operator e to the minus th. So that is also kind of operator from V to V. And this e to the minus th defined as a solution to the following differential equation. Let me give it a great name, u equal to 0, and u of 0 is kind of identity operator. So we have this differential equation for a family of operators u of t, and when t is 0, so this operator equal to identity, and when t is non-zero, so it solves this differential equation, and once again it is a kind of simple ordinary differential equation of first order, and we provided a kind of initial data. So then kind of Cauchy theorem tells us that there is a unique solution, and we denote this unique solution as e to the minus kh. So once again, if V is finite dimensional, so then we can treat this, so then H is some finite dimensional matrix. So we can choose some basis in V and kind of express this H as a finite dimensional matrix. And then we can treat this e to the minus kh as a usual matrix exponent. So in a finite dimensional case, we don't need to go through this complicated stuff. But unfortunately, for our applications, we will need V to be infinite dimensional, and that's why we need to go through this more careful definition. Because in infinite dimensional case, there is no kind of definition for matrix exponent, because there is no theorem that this thing would kind of terminate or simplify. So we have this operator U, or to be more precise, family of operators that kind of starts with this identity operator, and then for different t's, it is e to the minus t Hamiltonian. Yeah, unfortunately, let me erect the 7-term relation, because that's the only way I can get some more space. So we will remember this 7-term relation. Maybe I will write it like here, 7-term relation. For mu and g plus minus. And I will continue here. Okay, so we defined Hamiltonian, we defined this exponential operator, and now what we want existence of limit t goes to plus infinity for u of t. Okay, so u of t, it kind of by construction satisfies the following property, that u of t1 plus t2 is convolution, and therefore existence of limit. So existence of limit and this property implies that limit t goes to plus infinity for u of t should be a projector operator. So in a sense that p naught squared equals to p naught. So that is essentially this idea. If t1 and t2 both are very large, then here I have like if I kind of take say t1 and t2 to be t over 2 and take t to infinity limit, so then here this limit exists, I will get p naught, and here I will also get another copy of p naught, and therefore this convolution property together with existence of limit will imply that limiting operator will be some kind of projection on some subspace. So that is projector on subspace which we call V naught, which is subspace. Okay, so
we have already used V naught as the
Yeah, you're absolutely right. So I can say that my kind of gradient is upper script and not subscript. So one kind of property for related to this operator H is existence of leaf, and then property E is the property that G plus minus acts by 0 on V0. And this property can be formulated without even using V0, so equivalent formulation is this property that if I take a vector and project it to V0 and apply G plus minus, I will get 0. And similarly, if I take a vector act by G plus minus and then project it, I will also get 0. Okay, so that is kind of full list of long properties. So HTQM is collection of this data, vector space, pair of differentials, which are kind of G minus commutes with other differentials. Q and G plus doesn't commute in general and gives us some Hamiltonian, which defines a certain subspace. And then, in addition to vectors, super vectors, or graded vector space and pair of differentials, we have a pairing that also kind of compatible with a gradient. So if I interchange arguments in a pairing, we get the same result up to a sign. We get multiplication that is also bilinear in all arguments. It is kind of associative multiplication, so it doesn't have any signs if I don't change order of arguments. But it also graded commutative, so once again, if I exchange order of arguments, I get the same answer up to a sign that depends on a parity. So then Q and multiplication obey Leibniz rule, graded version of Leibniz rule. Multiplication and operator G plus minus obey 7-term relation. So G plus minus kind of looks like second order differential operator with respect to this multiplication. So then these operators, so if we take a pairing, if we act with an operator and then pair it with some other vector, so then we can flip this operator action to a other argument in a pairing at the price of having some sign, which is once again differ for Q and G plus minus.
Excuse me, do we have a reason for why this sign, one is like V plus one is like V2?
Yes, we have reasons for that. I think simple reason for that is that we want. So we have this Hamiltonian operator, which is Q and G plus, and it's kind of called Hamiltonian for a reason that we want it to be really kind of Hermitian with respect to this pair. So G H of V W, and then by construction H is kind of Q G plus G plus Q. And now to get this operator Hermitian, we actually need that flipping Q and flipping G plus would give us different signs, because here when we flip Q, we will get like some sign that depends on parity of vector V, but this vector V will be G plus acting on some other vector. So its parity is like a parity of V plus 1. But when we will flip G plus, we will flip on top of vector V. So there will be no kind of shift by plus 1. So therefore, in order to cancel these vectors, we need to have plus 1 in kind of relative minus sign between Q and G plus at least, and kind of G plus. So there is some other physical reason that G plus should behave in the same way as G minus. So here the requirement, so that is kind of lemma that kind of given this property and given this definition of Hamiltonian is a Hermitian operator. So it's kind of it's through this pairing, doesn't produce any signs. And to keep it, to make it Hermitian, we need to kind of offset this sign factors for Q and G plus.
Yes, if we require this H to be Hermitian, then there should be a sign here. But
no, the sign should be exactly offset by 1.
Yes, but if on the left hand side we set the same sign, then on the right hand side we will have anti-Hermitian H.
Yeah, but we want H to be really Hermitian.
And the reason from physics that this H will be Hermitian is what? Why do we expect H to be Hermitian, not anti-Hermitian?
If H is Hermitian, we can have real and
Real.
Yeah. So here I think the story is that usually kind of so. Let's say it. Okay, but okay, now I'm confused whether H is Hermitian. Give that a
The image is pure image.
Oh.
And here we want the existence of K equals infinity limits. That means the eigenvalue of H should be positive, non-negative, and real.
Yeah, I think that's probably a good point. That kind of like limit t goes to infinity for this kind of operator. Like if we manage to somewhat diagonalize this operator, so then existence of t goes to infinity limit, it kind of requires some bound on a spectrum of H, and this kind of spectrum of H better be something positive, because the limit e to the minus t lambda is only well defined when lambda is positive. So that's why we want like roughly Hermitian-like property for H. So that is kind of related to existence of this limit that is kind of one of the requirements of our HDQ. Okay, so now the kind of given this long list of properties, you may wonder whether HTQM exists. Like maybe these compatibility conditions are too strong, and only kind of empty set for vector space and zero operators and zero pairing is the only solution. But it turns out that the answer is not, and let me choose a different color and let me kind of start giving an example. So yellow will be example. So for a super vector space, it takes the following object. So that will be differential forms on some space X. And kind of we want to tensor it with n-dimensional lattice. So kind of elements here. So we will label them in the following way. So that will be a form in omega of x and integer vector. So that is kind of element from this tensor product. So it is a pair, differential forms and integer vector. So then V naught will be even differential forms multiplied by this vector, by this n-dimensional lattice, and similarly gradient will be odd differential forms multiplied by e to z. Okay, so for a pair of differentials, erase this part. Okay, so now I need to give you three differentials. So Q is very simple. So Q is essentially a Dirac operator that acts on differential form and does nothing to this integer vector. So it acts by d Dirac on omega and keep this integer vector. So once again, Q is odd operator because it takes like even form into odd form and odd form into even form, and Q squares to 0 because Dirac squares to 0. Okay, so now G plus. So we have this form omega vector m, and here we do the following thing. So we take a vector field that we already saw today, which is radial vector field with components equal to components of this integer vector. So I will like roughly write it like this. So I take scalar product of this vector m and a gradient vector. So then I take this vector field and substitute it into a differential form omega while keeping vector m unchanged. So once again, because we are substituting vector field into omega, so we are changing degree of the form by -1. So because we are working mod 2, like Z2 gradient, so this thing will also take even form into odd form and odd form into even form. So then, if I try to substitute the same vector field twice into differential form, so this thing is just 0. So that's why it satisfies this property that G plus square is 0. Okay, so now let me kind of yeah. So let's say that X here is toric variety. So there is a notion of decomposing it into radial part and angular part, because to kind of introduce this vector field, I need to decompose my coordinates into radial ones and pick up a vector field in radial coordinates. So because I have radial and angular coordinates, so I can construct a similar type of vector field, but using components of M as kind of components in the basis D over d phi. And once again, I can substitute this vector field into differential form omega and get a differential form with one lower degree. So that will also make it odd operator, and here the notation that G plus minus are similar type operator became clear because it's like plus and minus just exchanges radial and angular direction. Okay, so we checked these properties. So these properties are kind of hold automatically because Dirac differential squares 0 and trying to substitute the same vector field twice also gives us 0. So now what about this property? So this property also holds automatically because substitution of a pair of vector fields gives us the kind of anti-commuting thing. So IV1, IV2 substituting to omega is minus IV2, IV1 for any pair of vector fields. So this property holds automatically. So now the more interesting part is this property. So it's anti-commutator of Q and G minus. So here we can recall kind of Cartan formula that Lie derivative is an anti-commutator of the Dirac differential and a substitution of a vector field. So therefore, if you have a substitution of this angular vector field and anti-commute it with the Dirac operator, so then this operator would act by Lie derivative along this vector field m d over d phi, act on omega and keep m unchanged. So this thing is generally non-zero. However, we can modify our vector space by looking not over all differential forms on X, but looking at kind of differential forms that are invariant under U1 action. So that is kind of subspace, linear subspace in these differential forms. And these forms are defined precisely in a way that that Lie derivative with respect to any vector field from U1 to the power n, and vector fields from U1 is precisely basis in this vector fields is d over d phi k. So it means that Lie derivative with respect to d over d phi k for all k acting on a differential form is 0. So therefore, kind of anti-commutator of q and g minus on this space of u1 to the n invariant differential forms would also vanish. So here, okay, even invariant forms and odd invariant forms. So these invariant forms, they kind of naturally respect gradient. So there are like even invariant forms and odd invariant forms. And similarly, because Lie derivative commutes with the differential, so differential would also take invariant form into invariant form. So here the last property that we need to check that that kind of substitution of a vector field takes invariant form into invariant form. And for that, we can recall the following property, that if I look at the anti-commutator between Lie derivative and substitution, Lie derivative with respect to vector field V and substitution of vector field W, so this thing is a substitution of a vector field which is commutator of commutator of V and W. So now, by imposing this invariance condition, we need to check that if I substitute radial vector field, I still still get invariant form. And because this vector field m d over dr is kind of trivially commutes with m d over d phi, because d over dr k is commutes with d over d phi j, so any pair of these vector fields are commuting. So therefore, substitution of a vector field it kind of gives us again invariant form. So if I act by kind of Lie derivative with respect to one of the vector fields here, so it will still vanish on this object. Okay, and that's kind of the thing that we will need to check like later, that certain objects are kind of very naturally defined on differential forms, but we need to kind of verify that they descend to this subspace of invariant. Okay, so now, so that was vector space Q and G plus minus, and we verified these three properties, differential and anti-commutator properties. So now, what about this pairing? So if we have differential forms on some space X, and our toric variety is a compact space, so what we can do the following thing. So I need to erase some, but okay, let's erase here. So now I have omega 1 m1. So that is kind of object from my vector space, and I can omega 2 m2. So and I need to construct a number from this data. So the number is constructed in the following way. So first, we take the sum of these two vectors, m1 and m2. That is also vector in the end. And we check whether this vector equal to 0 vector. So if the sum of two vectors is non-zero, so then we just declare that the pairing for such states is 0. But if the sum happens to be 0, So then we look at omega 1 and omega 2 and perform the following thing. So we take omega 1, wedge multiplied by omega 2. So we get, once again, some differential form on x, or invariant differential form on x, and integrate it over x. So this thing is kind of defined on all forms, and in particular defined on invariant forms on x. So in this case, okay, we don't really need to do hard work in checking this property. Okay, so that is kind of our pairing. So it's usual kind of pairing of integrating differential forms. So because here we have a wedge product of differential forms, so naturally when we exchange these two arguments, we will exchange order here, and we will get precisely a sign that depends on a parity on a gradient of omega 1 and omega 2. And this property will be kind of important when we will verify some compatibility condition. Okay, multiplication. So for multiplication, we have the following thing. So once again, we have kind of an object which is omega 1 and 1. We have omega 2 and 2. And we want to multiply the thing to obtain, once again, object of the same type. And we can do it in the following way. So we wedge multiply differential forms, and we add this integer vector. So once again, because we wedge multiply differential forms, so this thing will get a correct graded commutativity property, because exchanging these things doesn't change anything in this integer vector factor, but it will exchange order in which we multiply differential form. So, and that will be precisely the sign that we want. And once again, because here we are using usual wedge multiplication, so it is automatically associative, because wedge multiplication is associative. So now we need to check whether product of two differential forms, product of two U1 invariant differential forms U1 invariant, and that is because kind of Lie derivative and wedge multiplication satisfy Leibniz rule. That kind of Lie derivative of omega 1 wedge omega 2 is Lie derivative of omega 1 wedge omega 2 plus omega 1 wedge Lie derivative of omega 2. And by assumption, omega 1 and omega 2 are both U1 to the n invariant forms, so it means that they have vanishing Lie derivative for any vector field from this U1 to the n. So it means that both terms in the right hand side are 0, so the product is also U1 invariant. So the multiplication kind of preserves this U1 invariant subscripts. Multiplying two U1 invariant form gives us U1 invariant form. Okay, so that is kind of our multiplication. So essentially we used some natural structures on differential forms like wedge multiplication, de Rham differential, substitution of a vector fields to kind of construct this data V, Q, G plus minus G, and mu. So now let us check compatibility condition. So Q is essentially the Rham differential. And mu is essentially a multiplication of differential forms. So this condition is kind of satisfied trivially because of Leibniz rule for the Rham differential and wedge multiplication. So the more interesting part is this 7-term relation. And I don't have like a simple argument why it works. So it's just kind of explicit check that we take this mu, we take this G plus minus, and we kind of carefully rearrange the terms according to expected signs in 7-term relation, and then see the cancellation. So this one kind of verified explicitly. Okay, so now let us go to this property that looked kind of a bit unmotivated or kind of motivated by some properties of Hamiltonian. So let us kind of see that actually in our definition we get exactly the signs that we want. So let me apply Q to the D. It means that we have D omega 1 and 1 and omega 2 and 2. So once again we check that M1 plus M2 is zero vector, and then we integrate over X E of omega 1 wedge omega 2. So once again, X is a compact manifold. So X is a compact manifold, so we can kind of integrate by parts this term to get X. And here will be with some sign. Okay, so and this so we can rewrite it like this. And the sign will be precisely kind of minus 1 to a degree of omega 1 plus 1. And that is precisely the expression that we got here, that we kind of act by Q on the second vector omega 2 m2, which will give me d omega 2. So d omega 2 m2. So that is what will happen if you act by Q on second argument. And indeed, we see because of this integration by parts, we get exactly a sign factor and with extra plus 1. So it means that if, say, differential form omega 1 is of even degree, so then we still get a minus sign because we kind of integral of total derivative is 0, which is sum of two terms d omega 1 wedge omega 2 plus omega 2 plus omega 1 d omega 2. Okay, so what about for d plus minus? So that is interesting. So let me okay, it doesn't matter which one I do. So let me do with G plus. So I substitute this radial vector field. Let me kind of schematically write it like this into omega 1 and keep M1 the same. And here I substitute omega 2 M2. So in this once again delta of M1 plus M2 comma 0 integral over X omega 1 wedge omega 2. Okay, so now I can do the following thing. So here I can't integrate by parts because it is not derivative. However, what I can do, I can okay, in some sense I can integrate by parts if I kind of represent differential forms as a functions on PTX, and then this operator will become a differential operator on PTX. So that is kind of one way to get in this kind of identify omega star of X as a functions on PTX, and then kind of vector field substitution would become both the odd differential operator and then the pairing, like integral of X would be like radial integral over PTX, and we will get once again some kind of integration by part. However, here we can do the following thing. So we can notice that if I take an integral over x of iv omega 1 wedge omega 2, I think this thing always vanishes. Okay, but I forgot what the reason for it. Let me double check my So there was some simple argument that okay. I think the simple argument works in the following way. So to get a kind of non-zero answer for an integral, we need to integrate top form. So it means that this object IV applied to a product of two forms should be a form of a top degree, like whose degree equal to dimension of x. But IV itself decreases dimension of form by 1. So it means that omega 1 wedge omega 2 should be of the form whose degree is kind of maximal degree plus 1. And such forms do not exist on X. So therefore, for any vector field V, integral over X of IV omega 1 wedge omega 2 is always 0 for kind of dimension degree reasons. So therefore here and IV kind of acting on a product of forms, it kind of obeys this property that IV omega 1 wedge omega 2 is actually IV omega 1 wedge omega 2, and then there is some sign that depends on quality of omega 1 IV omega 2. So IV acting on differential forms essentially acts as obeys this Leibniz property. However, here, like the object that we have is not just differential form; is a pair of differential form and m. So that's why on differential form it obeys Leibniz rule, but on this more complicated space, which is differential form times integer vector, it only obeys 7-term relation. So that is kind of important remark. But let us kind of continue this formula. So using these two properties, we can kind of integrate by parts and get the answer, which will be integral of omega 1, and here substitution of the vector field, which is m1 d over dr, because here for this formula vector field stays the same. And the sign here will be kind of the same sign as we get in this integration by parts. That will be minus 1 to a degree of omega 1 plus 1. But now, kind of to get G minus acting on a second vector, we need to substitute radial vector field that is along vector m2. And here we have a substitution of vector field along vector m1. But we can recall that in a pairing we require that m1 is essentially minus m2. So this term is not zero only if m1 equals to minus m2. So therefore here we can trade this m1 to minus m2 and use the property that the substitution of a minus vector field is a minus of substitution of a vector field into differential form. So that is a source of this offsetting minus sign. That yes, Q and G plus minus acting on differential forms only, they obey the same Leibniz type property. But because Q itself knows nothing about integer vectors, so it's kind of acting independently on integer vector assigned to a state. So it kind of keeps its sign when we look at a vector space which is the tensor product of differential forms and integer length. However, G plus and G minus acting on state, it kind of depends on integer vector assigned to this state. And therefore, to kind of flip G minus action through a pairing that ensures that only states whose sum of integer vectors equal to 0 pairs to non-zero number. So we will get this extra offsetting -1 for our G plus minus and G plus minus in Q. Yeah, so let me go maybe a few minutes over time to finish these properties. Yeah, so that was property 7. Okay, so Frobenius property is kind of rather straightforward because it's the usual Frobenius property for wedge product and integral of differential forms. That if I compose here this like 8, which is Frobenius. So if I first multiply forms and then pair them, so that will kind of give me an object of this type. So there will be like delta function that checks that the sum of all three vectors is 0. And here I will just have integral of x of a wedge product of omega 1, omega 2, and omega 3. And this expression is kind of manifestly graded symmetric in any pair of arguments. So therefore, this Frobenius structure is kind of satisfied in another simple way. So now we got this mysterious property 9, which is constructing Hamiltonian and constructing a limit, and verifying existence of limit and yeah, and G plus. Let me erase that part. So what is H? So H acting on state omega n. So what we need to do, we need to kind of compute QG plus G plus Q acting on this state omega n. And once again, like Q is Dirac differential, G plus is substitution of some vector field. So it's not surprising that the result of computation is just Lie derivative acting along this radial vector field defined by integer vector. So that epsilon omega and m stays the same. So now e to the minus th is essentially e to the minus t, e to the minus th acting on this state is kind of e to the minus t L and d over dr acting on omega and keep m. And this kind of Lie derivative e to the minus t Lie derivative acting on omega is essentially like evolution of omega in this radial direction. Okay, so here kind of for a kernel we get kind of the following interesting answers. So there are two cases. So one case is that our integer vector happened to be equal to one of the primitive normal vectors. So that's why we are in a situation that we kind of approach to infinity in a direction normal to this compactifying divisor. So in this situation, kind of because our form omega was kind of U1 invariant differential form on X, so it should behave nicely as we kind of go to compactification. So here, what we would get that essentially all differential forms, all vectors of this type, they belong to V naught. So if we kind of take a derivative in the direction of one of the primitive normal vectors, or actually any integer multiple of it, so then for any differential form we would get eventually 0 when we reach kind of compactifying divisor at t equals infinity. And an alternative option when m is kind of not proportional to b, so in this situation, kind of the only way to so then there is kind of another type of vectors in V naught, which are vectors when omega is a constant and sorry, maybe I'm wrong. Okay, so let me postpone this maybe explanation to next time. So yeah, okay, I think the final answer would be like 1b, and I think omega is 0. So if we have 0 vector, so then this Lie derivative, then exponent of Lie derivative just acts by identity. So therefore omega comma 0, in this case the limit exists because the operator for any moment of time t is just identity operator, and that kind of limit t goes to infinity of operator that is independent on t always exists. So these things are always in kind of V naught, and then if vector is kind of not proportional to b, then only kind of 0 forms for omega equals 0 the limit exists, and if vector equals to b, then the limit exists for kind of constant forms. Okay, so for constant forms, yeah, sorry, maybe I'm thinking. So if we have constant forms, so constant forms they do not change under the action of a Lie derivative. So therefore on constant forms this operator acts kind of trivially, so the limit exists, and if vector field is 0, so then on any form it also acts trivially, so the limit exists. So I think our vector space V naught is kind of generated by these two types of vectors. So it's constant differential form and any integer vector, or any differential form and 0 integer. So then, given this kind of explicit form of V naught, we can check this last property, G plus minus. So recall that G plus minus is a substitution of a vector field, either radial or angular, with components equal to components of integer vector. And if I try to substitute vector field into 0 form, I will get 0, because substitution vector field should decrease the degree of the form by 1. And if it's 0 form, there is nowhere to decrease the degree. So therefore G plus minus acting on these states kind of automatically 0, acting on 1 and 0. And similarly G plus minus acting on these states is 0, because we kind of trying to substitute 0 vector field into something. So more interesting stuff is kind of this property, that we first act by G plus minus. So it means that we substitute some vector field, say radial vector field, into omega, and then we project. But once again, we say that the whole V naught consists of these two types of vectors. So projection this checks either m should be 0, and if m is 0, then this term is automatically 0. Or alternatively, kind of the only other element that lies in this space, I think is element when we have a constant. Okay, constant we can get from substituting vector field into one form. Okay. Yeah, I think I did it in slightly different way. Yeah. So okay. So one factor it is 0 for obvious reasons, and another factor it doesn't look obviously to be 0. Okay. So let me once again leave it as kind of as something that I will as my homework. So I will do it. I will kind of resolve this issue next time. But kind of use some other way of verifying this property, and think they hold. So this one for sure holds, and this one kind of partially holds. At least I explained it partially, but kind of we verified that it is indeed also holds. So the kind of take-home lesson is that we give this very complicated, very long definition for HDQM, which is collection of this data vector space, pair of differentials, pairing and multiplication, obeying various kind of consistency conditions. Consistency condition like between the objects of the same type, like differential squaring to 0, or differentials anti-commuting in some particular way, or between objects of a different type, like graded Leibniz or 7-term relation, which is compatibility between multiplication and these differentials, and kind of compatibility between pairing and differentials. So a lot of compatibility conditions. But we showed that this definition kind of makes sense because we managed to give an example of a particular HDQM whose vector space is U1 to the n invariant differential forms on some compact toric variety X, tensor product with n-dimensional lattice, and Q is essentially the RAM differential acting on differential form and preserving M, and G plus minus they also preserve M, but they act as a vector field substitution to a differential form, and this vector field is kind of determined by components of M. And similarly way, we kind of used natural pairing on differential forms to turn it into pairing on these vectors from our vector space V by adding this additional kind of structure that kind of ensures that pairing is only non-zero when the sum of these integer vectors is 0. And mu itself is just multiplication on differential form and addition in vectors, and we kind of verified or almost verified all consistency property except this fancy one that P naught times this G plus minus times G plus minus whether this thing is 0. So if I first act with G plus minus and then project on this kernel of H. So that kind of concludes this story about HDQM definition, and with a particular example of HDQM, and this example of HDQM of this type with this collection of differentials is what we will later call A-type HDQM. So I think in a few lectures maybe not next lecture, but lecture after next lecture, we will see a different construction for HTQM, which will be B-type HTQM, that will be constructed in quite different way. So they both HTQMs will kind of share the same differential, but G plus minus pairing and multiplication would look quite different in B-type. And we will kind of introduce this B-type as a part of a mirror construction. Okay, so I checked a scheduler, and I think according to rules, if we're going to make final exam, which I think I plan to be like an oral final exam, so we should do it on a week 16, because week 17 and 18 they are kind of reserved for examination for undergraduate level courses. So, and I think before the week 16, okay, I think I have like, if I counted correctly, I think I have like 3 more classes. So I think it's 3 more classes, and then there will be final oral exam, and I think we will kind of get to this interesting part in. So next time we will kind of cover amplitudes for abstract HTQM and amplitudes for A-type HTQM, and maybe start resummation, and then lecture after that we will interpret resummation as a certain deformed HTQM that we will perform an additional T-duality and get into B-type HTQM, and hopefully on the last lecture we will talk about kind of localization to Landau-Ginzburg Saito model. So I kind of apologize that maybe remaining 3 lectures of this course will be a bit more faster pace, because I kind of really want to at least sketch the path towards the end point, which is Landau-Ginzburg Saito model, which we discussed in a great detail. So I really want to kind of connect this tropical pictures to Landau-Ginzburg Saito model. So I may need to kind of skip some of the details. So I kind of apologize for that in advance, but I really want to kind of give you a general idea of how the things are connected, even skipping some details. Yes.
How can h or exponential of h act on some m to be 0? I mean, this m is always preserved by this vector.
Yes.
So it's 0 if and only if the initial.
Yeah, but here we so V naught is kind of a subspace where this operator kind of acts by identity operator. So and this operator, like e to the minus th, is essentially like shifting radial coordinate by mt. And if you have a constant form, so there is no radial coordinate dependence, so shift by mt preserves it. So it means that e to the minus th acts by identity on this thing. Or equivalently, we can look at how g plus minus and q act on this state. So q acting on this state acts by 0, because it acts by de Rham differential. De Rham differential of a constant is 0. And similarly, g plus acting on this state also gives us 0, because we're trying to substitute a vector field into 0 form. So that's why these states, they are clearly in kernel of H. Whether you look, you kind of deduce it from studying kind of action of e to the minus th geometrically, or by studying kind of q and g plus minus action. So for this one, you don't even need cancellation, like both qg plus and g plus q act on this state by 0. So hence h act on this state by 0. And similarly here, so here the story is kind of more interesting because for general differential form, Q act non-zero on these states. But action of Q on these states, it kind of still preserves the zero vector. So therefore, when I will act with G plus, like when I look at G plus Q acting on this state, so Q will return the RAM differential, but then G plus will still substitute zero vector field into differential form. And this thing is zero by linearity. And similarly, if I act with G plus on this expression, I will also get zero. So therefore, this kind of families of states or this linear subspaces, they clearly belong to kernel of H. So I kind of haven't explained it that there are no other vectors in kernel of H, but I think these vectors are clearly in the kernel of H, regardless whether you analyze it from kind of looking at H action on them or analyzing by action of e to the minus th on these states and observing that e to the minus th preserves these states for all t's. So
I have a strange feeling that because in the beginning you discussed if this M is B.
Yeah. So sorry, that was kind of wrong. I think there will be some other type of states when it is 1 and this M is B that we will use to construct amplitudes, and I think it just was misunderstanding in my presentation, that I went like too far, that for amplitudes we also want to put like states from kernel of H on kind of endpoints on leaves, but it turns out that the interesting states that will have interpretation, so the states that will give us interpretation of amplitudes as a moduli space integral will be a situation when this M is not of arbitrary value, but equal to one of the primitives normal vector. So that is just some space in kernel H that we will need later. But to verify this property, we need like all states from kernel H and verify that it holds.
Yes, and the previous observables we introduced in our contents.
Yeah, so far there is no observables.
Yes, yes.
So observables will be some additional operators, all that will be like linear operators from V to V,
Yeah.
and observables are usually associated to some differential form and kind of section all gamma on omega n would be very simple. You just multiply your kind of omega that parameterizes your state by differential form gamma that is assigned to observables. So observables will be additional set of family of operators parameterized by differential form on X, acting in this simple way.
Yeah, and the two expressions of this V0 part is like it's like I have a strange feeling. It's like class, like homology class, something like.
I don't know. Maybe there is interpretation as some cohomology theory, but I don't know. So for me, it's just like once again, I think that is computed explicitly. So one of the things that we just computed and got an answer, and we were like happy enough with explicit answer, so we haven't thought about deeper interpretation.
This construction is very interesting, but I don't know what does this states mean. What's the meaning of this, guys? It's like you remember some velocity, and you also have some shapes as your differential forms or currents, and so. On the zero part is like there is no velocity, so it's like
so there is like partial interpretation. So remember we talked that if you have marked point, that we have some kind of observable gamma that we insert into this mark. And mark point was kind of treated by us as some kind of two-valent vertex. So here we can kind of imagine treating this thing as some kind of three-valent vertex. But for three-valent vertex, so here kind of being observable means that we preserve it this integer vector. And if we want to kind of treat this thing as some kind of three-valent vertex, so the only way to turn it into three-valent vertex is to somehow assign zero vector to this third leg that will carry our observable. And that's kind of a reason why on this state we would assign some kind of states like this, that we can kind of, we have a sort of state operator correspondence in this quantum mechanics, that kind of natural action of, so observable is kind of naturally associated to an operator because it is some kind of two-valent vertex, so it takes incoming state, acts on it, and get outgoing state. But also we can kind of represent this thing as some kind of product of states or multiplication by this state. So three-valent vertex correspond to multiplication, and action of this operator is the same as a multiplication by omega comma 0. So because multiplication kind of takes the sum of vectors on incoming state, and if in order to preserve this vector, we need one of the vectors on incoming states to be zero vector. So this kind of states, they are sort of dual to these observable operators under state operator correspondence. While these states, especially when m equals to primitive normal vector, so they are typical external states. So kind of before we insert any observable, so here we have like kind of trivial differential form, and we start getting some differential form dependence after we act on this state by this observable. So, but this interpretation will be more clear when we'll introduce amplitudes. So I think you are kind of running ahead of time, but there is some kind of interpretation for a vectors of this type, that this one is kind of state operator dual to observable operator, and this space is a kind of generalization of external states that corresponds to kind of pure divisor state. So it kind of just has only information about normal vector to hyperplane. So
yeah, so I noticed that this vector field is like gradient vector field for the quadratic function. Right?
Yeah, but this thing is kind of a stronger property than the gradient vector field because kind of every constant vector field is a gradient vector field. Not for quadratic function, but for linear function.
Yes. Yeah.
So
yeah, it's a linear vector field, but it's like the gradient for quadratic function, just like what we
No. So this vector field is a constant vector field. It's not linear. So a component of your vector field, like VI's, they equal to components of M, and they are constant. They are independent. So that's why we can get a constant components of your vector field if you take, given a constant, we give Euclidean metric on R.
Yeah.
So you can get it from taking a gradient of a linear function. So your function is something like mi ri sum over I. So then you take a gradient, you will get something like mi with some lower index, and then you use Euclidean metric to raise this index, and that will give components. So that's why it's not quadratic function.
Yes.
So in our other activity, we have we studied natural quadratic functions on toric variety. But here we rather want to study, if we want to embed this story into Morse story, that will be like a Morse theory for linear functions on toric variety, which is a different story than quadratic functions.
Yeah, and the reason for the first type of zero modes is the first entity is 1, is that it's like actually there may be some case that the first entity can be non-constant, but some kind of high degree forms. Then at that case, it's like an invariant.
No, but for higher degree forms, like Lie derivative preserves the degree of the form, so there is no kind of simple way to make it vanish. So this operator will just kind of
it just belongs to the zero the kernel of this Lie derivative.
Yeah, but we see, like, normally when we talk about Morse theory, and we talk about e to the minus TLV, so usually kernels are kind of generated by some Lefschetz symbols of the critical points. So if you have quadratic function, so quadratic function has idealized critical points. But if you have a linear function, then the gradient of a linear function doesn't have zeros. So for linear function, you just don't have critical points. So that's why the Morse interpretation here is much more subtle. Because here we have a linear function on Rn, and differential forms, they are not just differential forms on Rn, but because they are secretly forms on X, so they have a certain fall-off condition near compactifying devices. So that's why it is a kind of a Morse theory on a non-compact manifold acting on differential forms with a certain fall. So and that is very different from familiar Morse theory that we discussed in my previous courses on supersymmetric quantum mechanics, where we had a compact manifold and a vector field on a compact manifold. So this one should always have zeros, because the function, continuous function on a compact manifold always have like minima and maxima. So it means that you are always bound to have at least 2 critical points. And that's why, like here, you will at least have like Lefschetz samples associated to a minima and maxima of this function. But in our situation with a linear function of toric variety, the story is very different, because there are no kind of critical points, because we are acting on differential with some follows. So unfortunately,
form supported on those boundary computation, those boundary strata of the toric manifold. Is it kind of a form such that it is invariant under this Lie derivative? If it's supported on the infinity.
Okay, maybe let's say I think it's kind of very subtle. So maybe when M equals to B and omega is supported on HB, you can get something invariant. But that is a bit subtle, because these things require like carefully described compactification by these hyperplanes and
the reason why we exclude those stuffs is that the first entity is some kind of smooth, not kind of current, some singular supported.
It is kind of subtle. So it's kind of not an easy thing. So that was like long technical computation that we kind of carefully did for CP1, conjectured generalization for. Okay, so we did it for CP1 in a way that it is immediately generalizable for kind of CPN, and we conjectured that somehow our method would still hold for any toric. So that's why for us, like proof of this property that G plus minus P naught equal to 0 was a quite complicated technical stuff with a lot of subtlety. So I think. No, at least I don't know simple explanation. So for us, that was the kind of most technically complicated part of our paper. So that's why I still treat it as kind of rather subtle thing with this kind of a lot of issues and a lot of things need to be carefully treated. Okay, I think we should like really stop. It's like 1 p.m. So yeah, so if you have like more questions, please ask me in private.
Okay.
So I think we should like enter our class. Okay,
Yeah,
so
one private. For this interest the method is
we just call it A-type HTQM. So I think we invented it. So we gave it a boring name. So maybe in the future when if our papers get more cited, maybe we will get like Mayan and this name attached to it. But for now it's not that well known and well cited. So that's why it carries a boring name of A-type HTQM.
Yeah, it seems that now our construction only work in toric case because the second entity.
Yeah, but kind of all this tropical business only works in a toric case because remember when we talked about complex tropicalization, we need to perform different scaling for radial and angular coordinates.
Yes.
So it means that we should be able to make a choice of radial and angular coordinates on a complex variety, and that requires a toric structure. So toric structure essentially gives you decomposition of your complex coordinates into magnitude and phase.
Angular,
So if you don't have toric structure, then
work in real tropical case.
That's I don't know. So for us, the idea of the papers was not just abstractly study HTQMs. So this might be an interesting question by itself because we encounter these HTQMs in different kind of problems. But for us, this HTQM was just a technical tool to perform this mirror map. So that's why I think we set our goal to kind of get a clear derivation of mirror map. So and we kind of skipped all this philosophical discussion about other possible HTQMs and something. So
it's like for me, this vector space is strictly better than the drum forms or something like, because you remember some extra data, and it seems that these data are not true. Actually, it works for this science trick, and so it's strictly better than using drum forms.
Yeah, but in a sense, this vector space it kind of looks like a subversion of the RAM forms on a loop space, because in a loop space, like you can imagine your differential form expanded in like loop harmonics.
Yes.
And each harmonic is kind of labeled by integer vector.
Yeah.
So that is precisely and kind of coefficients in harmonics, they are like forms in X.
Yeah.
So that's why this vector space is kind of secretly resembles the vector spaces that we are getting in our problem, but with a different interpretation. That z to the n, it just labels. So if you look at the loop space on a toric variety, so then we can also realize it like as a vector space of a similar type, that it will be like differential forms on X plus kind of differential form for each harmonic. So that's why kind of secretly in a Morse theory case, in a Morse theory on the loop space, we kind of get a similar differential form, but I'm not sure whether our G plus minus they kind of act in the same way. So that I haven't verified. But forms and some kind of forms with additional level labeling by some harmonic, which is vector on integer lattice, that looks about right for our other problem. But we kind of agreed to postpone this discussion to like a separate discussion of this truncated loop space.
Yes.
So hopefully, if we go for HTQM for truncated loop space on truncated loop space, I kind of anticipate that we will get something of similar type, that it will be formed on X and
then the first entity will not be the invariant form, but
that I don't know, that is kind of more refined question.
then there will be no such.
But once again, on a toric variety, I think you can always like average over torus section. So it might happen so that even if we don't have U1 invariant forms, we can always kind of do kind of equivariant version of theory, which is essentially like averaging over U1 action to make like all operations invariant under this U1 to the power n that naturally present on a toric variety. So that's why I'm not sure whether it's something. So in this construction it looks something very mandatory, because without this property we can't have this thing. But maybe in the loop space case, maybe it's just some choice which we can make. I don't know. Like as I say, I haven't thought like carefully about it. So.
Sorry, just
Yeah, but what I think at 1:30 there will be class here.
I see. Okay. Yeah. Okay. Yes. Sorry. The mirror symmetry exists in this paper. It strongly depends on this existence of G minus.
Yes.
If it's real tropical case, then does it still exist some kind of mirror symmetry? Maybe a mirror symmetry on.
At least I don't know, and kind of at least I haven't seen in the literature that I read, but I read only some subset of literature in toric variety, but kind of Mihalkin claimed that he defined some kind of analog of Gromov-Witten invariance for real toric varieties, but I think he never kind of claimed some sort of relation.
So your construction of mirror side, the B
Yeah, so G minus will be important because the kind of B model differential will be constructed essentially by deforming Q by G minus commutator with some other operator. So okay, so I agree with it.
Okay. See you tomorrow.